Swayam Prabha. Digital India. Educated India.
Welcome back. So we start module 6. So this is the first, we are starting the machine learning part of this course, and we will start with introduction to machine learning. This is our first module, and then we will subsequently move on to different aspects of machine learning, or we will get into more further details. So lecture 26 is on machine learning basics. So the different concepts that we will cover is introduction to machine learning. Then we will talk about the concept of models. Then we will talk about the workflow or the pipelines that is required to construct a machine learning model. And then we will talk about some real world applications of machine learning in urban planning. So in today's context, every day we are listening that there is going to be subsequent change in the way we work, in the way we do our studies because of artificial intelligence and specifically machine learning as well. So there is always a confusion between what is artificial intelligence and what is machine learning. So basically artificial intelligence, machine learning is, sometimes we use the term synonymously, but machine learning is a subset of artificial intelligence. So, but more or less both of this enable system, both these systems enable us to learn from data and then adapt their outputs without explicit rule-based programming. That means earlier we used to develop programs where we used to specify exactly what is going to happen, and we create a set of rules in different ways, and then we get every time you give the data, we will get some sort of a output out of it, right? But we are specifying how it has to happen. But as soon as we go into the domain of artificial intelligence and machine learning, there is also like some rules, but at the same point of time there is chance to again form more than rules. That means we will get an output which learns from the data, generalizes from it, and then it can give its own predictions or recommendations. So this is how it is different from basic rule-based programming. Now we see use of machine learning every day. So let us look at some of the examples that we actually see in real life application of machine learning. First comes self-driving cars. Over here you can see autonomous vehicle detecting human beings, other cars and objects. It can recognize traffic signals, and then it is making its own driving decisions. So a lot of this is not exactly as per rules. So the system has to actually look into the input, and then it has to give a solution, and that can only be done when we form a set of rules which are generalized. That means exact input, and it may vary in different cases, but we can give a generalized solution which would be fit to that and which would be appropriate. So that means it is not exactly rule-based programming, but of course there are some rules, and along with that some amount of ability to predict based on some generalized principles. Then there is also facial learning, facial recognition. So every day we use it in security systems. We use it for unlocking phones. We use it for tagging people in photos in social media. Then there are healthcare and disease prediction that is happening, where AI-powered tools are increasingly utilized. That means we give it a set of inputs saying these are the symptoms, and then it can predict what kind of disease it is. It can analyze, this kind of programs can analyze the x-rays, and it can suggest what kind of treatments should be provided. But of course it can be again checked by a human doctor and so. Then in case of fraud detection and cyber security, where a lot of transactions happen very fast, and there are a lot of features in each of these transactions, different attributes are there which can be checked, and then using the ML can actually detect suspicious transactions. That means which is not normal. So there is normal set of transactions which happens every day, and then there is something which is not normal. How to detect what is not normal, right? So it cannot be based on rules, because we don't know what kind of intrusion has happened, what kind of code is being utilized for trying to hack into the system, but it can understand this is not normal. So up till that. So that means it's an intelligent detection. Then there are virtual assistants and chatbots. Like there are AI-powered assistant answer queries, set reminders. That means an AI-powered assistant can give answer to queries. Mostly the queries doesn't need to be very specifically determined, but still based on the the general direction of the query, it can give answers. Then it can set reminders for certain activities, and it can also control smart devices. Then there are recommendation systems like which can suggest you movies, products, or music based on your preferences. That means it learns from your earlier choices and then it can predict something. Then there is time series forecasting where ML models can predict stock trends based on historical data. So it looks into the data of over different time periods and then it can predict. So coming to detailing out, along with artificial intelligence and machine learning, there is also another term, deep learning, which is increasingly being used, and people sometimes confuse between all these two. To make it very clear, we can say that artificial AI refers to the development of computational systems that can perform tasks requiring human-like reasoning, perception, decision-making, and adaptation across diverse problem domains. That means it refers to general set of tasks where there is human-like reasoning, perception, and so on. Then there is machine learning, of course, which is a subfield of artificial intelligence. That is where mostly we are dealing with data. That means the system learns from patterns from the data and then improve their decision making or predictive performance through experience rather than explicit rule-based programming. So this is the main part that we are going to deal with in this particular course. That means we have a set of data and we have to understand or analyze the data, understand patterns from it, and then using the data I can predict outcomes that what should be, or we can also predict policies, or we can also predict recommendations, right? And it is again not based on rule-based programming, but there are certain rules we have to follow, of course, but we will be able to give more generalized solutions. Then there is deep learning, which is even a branch of machine learning where specifically we use neural networks, and particularly in deep learning we use multi-layered neural networks. And this architecture of the way that we are trying to analyze the data and then we come to a solution, it is known as this neural network, and sometimes it is again treated as a separate field within this domain of machine learning. And it is where we the way human beings reason, the same logic is being utilized to automatically learn increasingly more complex abstract features from very large and complex data sets. So to summarize, AI is the overarching concept and ML is the subset of that particular area of or the domain, and where particularly we are focusing more on data driven learning. And finally, deep learning is even a specialized class of ML. Now before we go into details of different types of methods or models that we use in ML, we need to have some fundamental understanding. That means because we are dealing with data, of course we need to do analysis of the data, right? So we start with exploratory data analysis. We have been already showing you that in the previous lectures, where we are using Python program to do the basic calculations and all. But now we can move into more complicated calculations where we are trying little by little, we are moving towards trying to generalize outcomes from the inputs that we are being given. So EDA is summarizing, visualizing, and understanding data to uncover patterns, anomalies, and relationships, which has to be done even before developing models or before modeling, right? So this part we will learn along with introduction to machine learning. And then in the machine learning, core machine learning part, what we will do is we will learn the process of building computational models that can learn relationships from data, and by after learning that relationships, what we can do is we can use that model to take another set of data from another location or from another time or from another even another context, and then we can use the same model and to make predictions. So that means predictions would be based on new data. Now of course the context has to be almost similar, but if the context is totally different, of course we have to build another model. So the model that is built is based on data, and we try to get a generalized solution out of that while building the model so that it could be applied in some new data. So machine learning focuses on learning models that generalize beyond the data. Now coming to models, models are abstraction of a real world process or mathematical representation of reality. So what it does basically is, if there is a environment and then there are certain changes that is happening in the environment, I want to predict that changes that will happen, right? Or it could be not, it could be a situation where a machine is operating, it is doing certain kinds of things, and that steps that it takes, what results it will give, right? Sometimes depending on the complexity of the steps, the output that we will get would be different in each case, but the model will be able to predict that. So, but in most cases, it is like we want to predict something, we want to try to get to know what will happen earlier, or rather, if we want to predict that, okay, this particular group of data, it belongs to which class or which group. So those kind of things could be predicted by using machine learning models. And these models are basically what it does is it maps the inputs. That means input means I will give some data as input, it will try to learn from the data, and then it will try to first look into certain, if there are some outputs already known from older data, it will try to map these inputs into outputs, and then it will change, it will create that function, or it will try to modify that function that we are going to use at the back by tuning the different parameters of the function, and then that will result in a proper prediction. That means machine learning models mostly focuses on predicting what will happen. Now, what are these learn parameters? Now, of course, that means there has to be a mathematical representation of the process that is happening for which we are going to predict something. So within that particular mathematical formula or that process, the different adjustable quantities that are there, that means within any kind of equation there are some parameters, there are some coefficients. So we can adjust those so that the prediction is error free, or rather it will minimize the prediction error, right? So learned parameters are basically adjustable quantities within a model that are estimated from data during training to minimize prediction error. Now what is that mathematical equation? Now let us take a situation where we are trying to predict y based on x. So that means x may be money and y may be that means the income of a person, right? And y may be some kind of behavior, like for example, will he buy a car or not? So if I try to buy, that means for a particular person, if he is willing to buy a car, it could be, or will he buy a car in his lifetime, depends on his income. So if his income is very low, he will not be able to, right? So how do I generalize it? I may assume that, first of all, that these two variables are linearly related, right? So I will predict that, okay, the mathematical function will be linear, right? So here you see model y equal to beta 0 plus beta 1 x plus the error term. So what we are trying to do is, if I adjust the, and as you know that beta 0 is the intercept and beta 1 is the slope, right, in a line. So that means if this is a regression line, that means this slope is the beta 1, and this intercept, if the regression starts from over here, this becomes the beta 0. So this is the intercept. So this is the x-axis, this is the y-axis. So in this case, we are going to change the values of beta 1, beta 0 and all these things, and gradually when we do that, eventually we arrive at a situation where the model will be able to predict by, and the errors that will be resulting because of that prediction would be minimized, right? So this is what is meant by making a model. So in case of urban areas, urban systems are pretty complex, and in many cases the models are not linear, those are non-linear, right? So sometimes we want to simplify by assuming linear equations, but sometimes in most cases many models are non-linear, and accordingly we have to change the assumptions, or rather the equations that we use to train that particular model. So, or sometimes it's not even an equation, it is done in such a way, there is of course mathematics at the back end of it, but it may form like the steps that we form, it's a combination of certain rules and certain equations and so on. So and because these are non-linear and there is many variables, so they interact with each other, and this simple rules cannot capture the uncertainty or the dynamics, and so that is where we will end up in very complex models. So obviously there is no fixed algorithm or a fixed mathematical function, so we use different algorithms, which is again a mixture of mathematical functions and logical steps and certain kinds of other kinds of other kinds of approaches or theories that we will discuss in the next lecture. So other foundational theories which are utilized to develop this sort of algorithms. Now different problems require different algorithms. It requires different analysis, and of course the data sets are also different. So we cannot use the same approach to all problems. There has to be different approaches, different models. And then the so within urban informatics, the particular subject, machine learning is one of the most important part, and that's the core part, because that is used for future predictions. And we are moving on from descriptive to predictive analytics. That means earlier we used to describe the data, that is we go for a survey, we say that this is the modal share of in a particular corridor, we say that so much percentage is car, so much percentage is bus, and so on. Now that is very descriptive, right? Now will that be repeating that same that percentages will continue to be there in the future, or are there several factors which is influencing that, and using those factors I can build a model which would be able to predict the percentages of vehicles in the future, which would be different from the current percentage. It may be same also, but it may be also different. So we are moving into predictive analytics in machine learning models. When we say we are building a model, now models were there. Now machine learning allows us to introduce more new techniques or many new approaches using which we can build very complex and very strong models. So then using these models we can have automated decision support systems, and we can analyze the past data, and we can use it to predict the future. So this is the benefit of developing models. Now building a model is not a simple task. That means I just start with data and I immediately write a few lines of code and the model is built. Well, that is not how we construct a model. The model workflow has to be developed very in a structured way. It cannot be just taking data and then trying to fit a regression equation or any sort of a equation and then saying that this is the result. So that's not the process. It's a detailed process which requires a lot of detailed critical analysis and so on. And sometimes we use the word pipeline, like workflow or pipeline, but sometimes in Python language itself there is something called a pipeline, where we actually list the different steps that has to be done together, and then we call it a pipeline as well. We will learn that as well later. But in general, there is the workflow basically refers to the way we should approach building a model. So of course, where we start with defining the problem, right? For example, if I look into the data set which we were using earlier, we were predicting the air pollution levels, so say predicting PM 2.5 levels. So that's our problem. That means that is our target, right? Now then what we have to do is we have to look into theory, we have to do literature review, then we have to use our intuition. If there is not too much literature, then we have to also use our intuition, and then the domain knowledge from this field will help us to use our intuition, and then we have to frame our hypothesis, right? Now framing our hypothesis, already we learned what is how to frame hypothesis and all. What it basically says is, that means we will say that I will try to find the link, what is causing this pollution to happen. So obviously one example could be traffic pollution. So that means my hypothesis is traffic pollution is linked with excess amount of PM 2.5, right? So that's my hypothesis. And alternative hypothesis, null hypothesis, all these things also could be constructed accordingly. So once we have developed my theory, that means I have a hypothesis which is saying that these are the things which needs to be examined. Then of course we collect the data. That means, or rather, if the data is already there with us, already collected, then we can use that data. Either we collect from sensors, or we use APIs to get the data from other institutions or other organizations. And then what we look into is, once the data we have got, we need to analyze it for the quality. That means how good the data is. That means Is there missing values in the data? If so, then I have to fill up those missing values. Is there bias and noise in the data? That means is there a lot of outliers in the data? Is it like the data is collected, but there is this collection bias? There are different kind of bias, of course, but like for example, there is a error which is repeating again and again, and then there are measurement errors, like like some value is coming wrong because of some issues. So like traffic counts, for example, right? There may be a lot of noise in the data, right, if we are not careful. So and during certain times of the day there may be more variability. So all these things we have to look into before we start using the data for analysis. Then comes the data pre-processing part. That means this is where once we have understood what are the problems, then we need to take steps. So this we call cleaning of data. That means we can put in the new values, we can sort out the outliers, we can remove the outliers from the data, that means which are beyond 2SD or even beyond that, or earlier we have seen that we have taken certain values to, or certain kinds of analysis has been done to remove the outliers and all. So this is what we have learnt about this. And sometimes we also need to scale the values as well. That means we cannot use the values directly. I need to scale them out so that all the units comes down to could be measured in the same way. For example, air quality, or traffic pollution, traffic count, which is the number of vehicles, or maybe we can look into the greenery, that could be NDVI index, many things could be there. So we want to normalize the data, right, so that we want to scale it. So these are the steps, and then once we have done, the data set is ready, then we first is to divide the data set into two parts. One is for training and the other is for testing. Why? Because I need to test if my training that is or the model that I am building, when I apply it to some new data set, new data, it will be able to do proper predictions. So once I train the model, that means we learn from the data and we evaluate that, and then once we have learned and done all these things, then we will build the model, and once the model is built, then we use that model to do predictions, right? So that means usually there is a 70-30 split that we do. That means we keep 70% data for training, and then we can again use the remaining 30% for prediction. And then there, in addition to that, there are many other steps how we can improve the performance of the training part by dividing the data set, or sometimes we generate new data when the data is sparse by bootstrapping, or sometimes we take divide the data set and then we develop different models from those divisions, and then we try to take the average of those or try to generalize in that way. Then after we have decided on the training, testing and all those divisions of data, we start building the model. And before we start building the model, we have to do some assumptions, because sometimes I know the distribution, sometimes we are not clear about the distribution. So we construct scatter plots to see how the data is related with each other, if there is collinearity, or what is the distribution of a particular data, is it following normal distribution. Basically all this will govern the nature of the relationship. If it is linear or non-linear, it will govern what sort of mathematical equation would be used to represent that. For example, if the data is linearly related, if two variables are linearly related, we can go for linear regression. If it is not, then we can explore other non-linear regressions as well. Then after that, the next thing comes is what are the relevant input variables, right? Now there are two ways to do it. One is we start whatever we are assuming at the beginning that this has an impact on PM 2.5, we can put all of them in the equation, regression, and then, or rather we can test them. We can test that, okay, what is the significance of this particular variables? Are those really making an impact? And we can remove some of the features as well, right? Some feature removal could be based on theoretical understanding of that particular problem. The other could be based on statistics as well. So after all these things is done, then we train the model. That means we learn the parameters from the data, or we rather determine the beta coefficients and all this. And once this is known, then what we can do is we can use this model that we have built for new prediction, that is predicting the future pollution levels of a particular area. That means if I know the traffic count of another street, if it's a simple linear model, I would be able to predict the future pollution of that particular street. So once we do that, after we do the prediction, then we can measure that, okay, how good our prediction is. That is, we use some matrices to do that. We will learn those as well later. So there could be RMSE, then there could be R square, so coefficient of variation, then root mean squared error. So all these things we can use. Then there is map as well. So using those we can evaluate how good are our predictions. And once we say that, well, it is all okay, acceptable, then we can stop there, or we can further generalize by like applying the model in some data set in another city, and we can, or sometimes what happens, some features of the model, like if I see that that there is some division could be done in the data set using spatial variables, that is this data comes from this part of the city, this data comes from this part of the city, I can do some spatial generalization as well, right? That means the model is developed and tested in two different spatial areas. So all this validation, generalization needs to be done, but first, of course, we have to interpret the results. That means once we look into the coefficients of the model or the importance of the features, we will understand, does the predictions is related with our theory. If it is not, we call them, suppose, for example, when traffic increases, pollution increases, right? But if it so happens that, well, when traffic is increasing, I'm seeing pollution is decreasing, right? So that means it's counterintuitive. That means it is showing something which is, opposite. There may be a reason for it. We can try to explore that. But if we don't find a reasonable reason for it, that means there is some error or so on. So we have to see there may be multicollinearity over there, right? Maybe there is another way. If I remove one of the variables which are related, then the prediction will probably improve. The signs would be stabilized. So once we are okay with all this, then we do finally do proper validation generalization, which will say that, well, the model is very robust, it will be able to be predict in other cases, other time periods, other areas, and then we are satisfied with the model. Then we deploy the model, or we do our decision support system or policy planning, whichever is required, using this particular model. So this is how we build a model. And the model learning part particularly depends on, one part is, of course, the equation that we choose, or what kind of model we are building, and then there is something called the model learning. That means the model itself, these beta parameters are adjusted in a sequence of steps to arrive at the ones which is showing the least, the errors should be reduced, right? So a model iteratively adjusts its parameters to reduce prediction errors based on a loss function. That loss function is that mathematical function that we are talking about. But again, at what rate it would be loose, so those things are there. So gradient, that there another term comes into play, that is called gradient. That means how I will change, how will I fine tune this, arrive at the final, this beta coefficient by making adjustment, in what steps the adjustment should be made to the beta value. So that is the gradient part, right? But the loss function is that equation which will generate a cost at the end of it, and we can minimize that cost or that error, and based on that we can arrive at the final model. Then talking about overfitting and generalization, what happens is, if I am training a model on a data and it very nicely fits on the model. Now when it happens, if you remember, when you do a linear regression, we may get a that R square value of 7 or 8, right? But if I use a higher order regression, right, a polynomial regression of square or cube, that fitness increases, right? But we have introduced more complex terms, right? Or if I keep on adding new features, which I think is having an effect on the final outcome, again the model would become better. Maybe it will improve. The prediction R square values will improve. But what happens is, when I take this model and apply it to some other city or some other area, it may actually give us very poor results, right? So this is the problem of overfitting. That means the model fits into the training data so perfectly, it fails to predict properly for the new data set, right? So there has to be a balance between this trade-off. That is, how much complex model has to be made, or how much not how many features you are going to introduce into the model, how complex the model is. Between that, and also how the model has to be more generalized, it can predict all outcomes, even when the model structure is pretty robust. So to find this trade-off is this bias and variance trade-off that we will discuss later. Now, trying to summarize very quickly what are the machine learning applications in urban planning, and of course in today's context we are every field we are seeing introduction of machine learning, and urban planning is also we are every day we are seeing new applications of machine learning in urban planning. And we can use machine learning for land use modeling and urban growth. For example, any kind of city, there are different problems, demographic related projection problems, economic prediction problems, land use distribution for new areas and all these things. So many kinds of problems are there. So we can do different types of analysis. So we can use logistic regression, random forest, linear regression. So this is where we have a set of data and we want to predict something, the outcome of it, right? So this kind of models would be utilized. Then sometimes we use like optimization, hybrid models, machine learning and optimization together to do some predictions on what should result in good, outcomes, right? So what is the optimized value? Then forecasting future urban expansion, we can use like models such as cellular automata, where we try to we divide the entire area into different cells or different zones, and we can say that, well, how that zone is transforming over time. I can build some machine learning models to create those, the chance of transformation. And the cellular automata modeling framework organizes these predictions and see how this transformation affects the entire area, and we can see that, okay, how the area will change, right? So it's a mix of both hybrid models and cellular automata models. And then we can also detect, we can analyze the images like satellite images and all from different time periods, and we can say that, well, how this area is growing. So this is where we will use CNNs or convolution neural networks and so on. Now for infrastructure design optimization, we can everything is now becoming data driven. That means if you require something, if there is a problem, or that can be predicted using a regression model, or we can try to optimize a certain infrastructure to improve its efficiency, sustainability. There again we can go for optimization and machine learning hybrid models. Then for predictive maintenance of urban infrastructure, I can have fit sensors into a bridge, and we can measure the vibration. The more time goes, the vibration increase. That means if there is some errors, some problems that is developing in the bridge, and that means I can predict that there is a maintenance required and so on, right? So we will put sensors and we can monitor the data coming from the sensors, and then we can see that how that changes over time. And this is where we can use time series models like ARIMA, LSTM to predict what is going to be the outcome. And if I can do this automatically or at certain time intervals, I can prevent failure, and also that means we can reduce the life cycle cost and we can improve the safety. Then to predict failure versus no failure, that is we can also use classification models. That means we can say that, well, this infrastructure based on these features will fail or not, right? So this is where we use, it's a classification task. That means we want to assign that particular group, that particular new features into a particular group, right? Will it fail or not? So this is where we can use random forest, SVM and so on. Then we can use for environmental impact assessment. Again, we can use regression models to predict some impacts based on certain features, certain changes which we are recording. Then we can also do regression models which are geographic regression models. That means spatially the model parameters would be varying. That means for different locations the model structure may remain same, but the attributes would change, right? So we can do assessment of location specific effects of air quality, noise levels, many things, right? And sometimes we can also do scenario based ML models. That means we can create scenarios, and then using those scenarios we can do predictions of what will happen and so on. So this is very important in EIA assessments and so on. Then we can use machine learning models for urban heat island analysis and mitigation. We can use CNN models with satellite imagery. That means to identify which areas we are seeing more amount of heat accumulation, where temperatures would be more. And of course the satellite would be thermal, image which will have information about the pixels will show the temperature difference, right? Then analysis of building density, surface materials, land cover to predict temperature. So we can go for a regression model. Then for hotspot identification, that means within a city area, certain areas are hotter, certain areas are cooler. So which zones are hotter than the nearby zones, or which areas are cooler than the nearby zones. So here we use clustering models. It could be K-means clustering, then DB-scan clustering, and so on. Then air quality monitoring and pollution control, again we can go for time series modeling for predicting long-term and short-term effects of a particular, using different features, or it could be clustering models. Then building design and energy efficiency and all these things, this all could be also analyzed. That means we can do very complex model where physics is involved, right? That means, for example, you want to use computation fluid dynamics to understand how wind flows in different parts of the room and what could be changed and so on. So that means it requires high dimensional models, right, which could generalize from very complex data sets. So that is where we will go for artificial neural networks, where complex building physics simulations could be, physics equations could be utilized. And then we can predict electricity demand based on time series data. Then we can optimize energy distribution via load management, and this could be done using reinforcement learning. Now reinforcement learning is something where the model or that program trains itself by changing certain aspects and see what the result would be, and based on that it gets a reward or some sort of a learning happens in the form that, okay, certain steps will have reward, certain steps will not have, and then the program learns and says that, well, in a particular state or a particular situation, this is the steps that I have to follow so that I can reach the final outcome, or I get the maximum reward. So this kind of strategy is reinforcement learning. So that also could be utilized. Then it is used for public safety and crime prediction. For again time series models, we can go clustering of identifying high risk zones, and then we can also go for preventive strategies or risk predictions using classification models, logistic regression, and so on. And then disaster management, risk assessment, all these things also requires machine learning models. And so there are hybrid models which can involve some physical models like physics or certain kinds of equations which has been developed, which will be used along with the machine learning models to predict floods, heat waves, earthquakes, and so on, which are not linear structures, which are very complicated structures, and then these has their own set of models which are very complicated to predict those kind of outcomes. Then risk mapping, vulnerability assessment could be done. Then emergency response planning could be done, and so on. So a computer program, now I will end. So now that we have understood what is machine learning, I would like to end with Tom Mitchell's statement. He's sort of, he's the godfather of, he's one of the most popular writers for machine learning. A computer program is said to learn from experience E with respect to some task T and performance measure P if its performance to task T as measured by P improves experience E, right? So that means the performance has to be measured and it has to improve, right? So that if a program can do that, obviously we can call it a machine learning program. So these are some of the references which you can utilize or you can study further. And to conclude, machine learning provides a structured data-driven framework for modeling, predicting, and supporting decisions in complex urban systems. Thank you.